I'm Doug, and I am here. Yes. Yeah, it worked this morning, too. Thank you. But more formally, my name is Doug Stevenson. I'm a developer advocate with the Firebase team. I work very closely with them. I also do a lot of Android development, so I'm excited to see how Firebase works well with Android. In this talk, I have source code and an actual app that you can look at. If you study all the source code, you'll know everything that I'm saying. I won't surprise you. In fact, what I'm about to talk about is actually a step down from the source code. But I will explain a little bit what's going on in there. By the way, the app is a few steps short of the source code. I had signing key problems with my app, so I couldn't publish the latest version, but you can build it and run it for yourself. For those of you who don't know, Firebase is Google's mobile application development platform. There's a ton of things in it, a bunch of APIs, a bunch of services. I'm not going to talk about the whole thing today. There are two in particular that I'd like to talk about, Firestore and Realtime Database. They are both cloud-hosted, real-time, NoSQL databases. What does that mean? Well, cloud-hosted means all your data lives on Google servers in the cloud, so you don't manage it, you don't have to scale it. It's real-time in that writes that you put into Realtime Database and Firestore can get distributed to clients immediately. And it's NoSQL, meaning there's no SQL commands. It's all documents and flat JSON structures. To visualize this a little bit better, you could think of real-time databases as all interconnected with the client. So if one client writes up into the database, all the other clients that are listening at that location, meaning they're observing some location in the database, will get invoked immediately to see those changes, which is really convenient for writing things like chat apps or anything where you need database that's live. You know, not just a query and one set of results, it's a query with live results. I work in developer relations, and so I'm a developer advocate. We also have tech writers. We have people who we call developer programs engineers. Between those three roles, we make sure that Firebase is easy to use. So anything that you see on the website was probably written by us. All the sample code was written by us. All the videos are done by us. That means we generate a lot of sample code. So you might see something like this. This is a typical simple example for Firestore. So with Firestore, and we'll just go through this line by line, reach and get the singleton instance of Firestore, then we'll grab a collection called collection. We have a reference to that collection. Then we're going to get another reference to a document inside that collection. Now we're going to call get on that. And get will return either success or failure. Pretty straightforward example, right? It's pretty typical API. But this may raise a lot of questions for you. So you might say, well, who manages this singleton? Am I using dependency injection? Because dependency injection is often what you use to manage singletons. But this source code says nothing about that. You might say, well, how am I doing asynchronous programming? That get returns immediately. Those callbacks are called sometime later when we know there's a result or there's an error. So what's the best practice for doing asynchronous programming? Or you might also ask yourself, do I update my views here? Once I get my data, should I just reach right into my views? All of our samples don't really have much to say about that. Firebase is not opinionated about the architecture of your app. These are all great questions to ask, but they're all questions that are ultimately dictated by your application architecture. So you can think of it like this. There's Firebase on one side, and there's your views on the other side. Everything else in the middle is your app architecture. Firebase is generally not too concerned about that. It's not opinionated. And you have a lot of choices here, right? So you've probably heard of MVC, MVP, MVVM, QVC, FTP, I don't know. Whatever's in the middle there is whatever you choose in the middle. Firebase is agnostic about that. But you might ask the question, well, what would Firebase do? Is there any recommendations from the Firebase team? Formally, there are not really any recommendations, but for Android apps, the Android team has a lot of opinions about that. So you may have heard that there's a new library. Well, it's not really a new library. It's a conglomeration of libraries, some old, some new, called Jetpack. With Jetpack, these are your tools for building out an app architecture in the way that Google thinks you should build your app. And again, you can take it or leave it. This is for you to use if you want to use it. You don't have to use it. A lot of people are nuts for RX, or there's a bunch of other options out there. But for my money, I'd rather use what Google offers. So there are two in particular. Actually, I have samples that deal with paging, Work Manager, Data Binding, ViewModel, and Live Data. But the two I'd like to talk about most today are Live Data and ViewModel. This forms the foundation for what you would call reactive programming in an Android app if you're using Jetpack. With Live Data, basically what it does is it gives you a vehicle to notify views when the underlying database changes, which works really well with Realtime Database and Firestore. The very definition of Firebase or Realtime Database and Firestore is that clients can receive updates that happen in your database immediately. And with ViewModel, you can manage UI-related data in a lifecycle conscious way. And that's a kind of a sound bite definition. I'll go into more what that actually means for your app later. But if I may remind you, with Firebase, Realtime Database, and Firestore, actually, I'll just say Firestore. Firestore is the new hotness, so I'll just sort of talk about Firestore mostly. With Firestore, again, you're writing a document into Firestore, and the clients can get that immediately. This is what Live Data does. Live Data's pure existence is to do stuff like this. Now, all the examples you'll see on Jetpack deal with Room and a SQLite database. I'm going to extend that to talk about Firestore. And what you can end up doing is building apps like this that are showing data in real time. So if you focus your attention off to the right, you'll see these numbers are updating in real time. And this is an actual screenshot I took from my demo app. So you can think of this as sort of like a live, real-time stock tracker app. So the way Firestore deals with its data, and this is kind of peculiar, this is unique to Firestore, makes you define collections. So this is an actual screenshot of the Firebase console. What you have here are 3 columns. On the left column, you have collections. So there's one collection here called Stocks Live. And within that collection, you have a bunch of documents, and these are the IDs for their documents. These also happen to be the fictional tickers for the IDs. And then on the far right, you have 2 fields. So each document has a price and a timestamp field. And if you go even further, this document actually has collections organized underneath it. So recent history is a sub-collection of each document. If I click into recent history, it shows over here as a collection on the left, and now I have a bunch of time-stamped documents, which is each one of the individual ticks that this stock tracker made, and then there's a price and a timestamp under that. So this is what the schema looks like in Firestore. I also did this in Realtime Database in parallel. The structure is a little bit different, but this is what you can expect in Firestore. So the question is, how do I build that other app, that stock tracking app, using Firestore and also Jetpack components to sort of plumb that data? Well, one thing you could do is, this is without using Jetpack. Here's how you would write the code to get stock price changes from a document, any one of those documents in Firestore, into your app. So the first thing you would do is grab the Firestore singleton instance, reach into the collection, reach into a document in that collection, and then add a snapshot listener. And that snapshot listener is going to receive a snapshot or an exception. One or the other, not both, not neither. So you have to check which one it is. If you do get a snapshot, you can then create a model object from that. So I have a stock price data class, and it has 2 fields in it, ticker and price. So the ticker is just the 3 or 4 letter ticker, and the price is that float. If there's an error, you'll have to handle that as well. And to keep this simple, I'm not going to do anything with that error. You should handle errors. I'm not handling errors here, but I'll say a little bit more about that later. Once we have a model object, then what we can do, in theory, is reach into some text view and just set the value in there. So we'll take that string from the model, the ticker from the model, and put it in the text view. You could do this. This is totally valid code, but it's also poor architecture. One thing that all app architectures generally agree on is your data source should know nothing about your views, and your views should not know anything about your data source. There needs to be a level of abstraction between those. If you've ever written code like this, you end up with activities with thousands of lines of code in them. Has anyone ever written or come across an activity with thousands of lines of code? Okay, like everyone in the room. Okay, yeah. So actually, one of the first jobs that I had as a professional Android engineer was 7,000 lines of Android code in an activity, and it was darn near impossible to factor out. Anyway, so let's not do that. Let's use good app architecture from the beginning. So let's use live data for that. So a little bit about live data. If you know observable objects, live data is observable. So if you already know about observable objects, you kind of get an understanding of what live data is. So you can attach observers to it, and those observers get notified whenever the data within the live data changes. They're genericized, so every live data instance has to say what type of object it's going to deal out. You can't not do this. Every working live data must specify a generic type. And they're lifecycle aware, so it handles component stop, start, destroy states automatically, and I'll go into more detail about what that means. But the good thing is they will not leak activity instances. I'm sure you're all familiar with leaking activity instances if you've ever run out of memory and had that tracked down to a large monolithic activity that did not get garbage collected. So what can we do here? So let's take a very basic boilerplate activity. There's an onCreate. We're going to inflate some views, and we're going to pull some views out of that. Pretty standard stuff for an activity. Now, say we want to use live data here. So what we're going to do is get a hold of a live data, which is parameterized by stock price. You remember that stock price object is a data class with a ticker and a price. And I'm going to be a little bit hand-wavy about how we get hold of it. So let's just say there's a method out there that grabs a hold of this live data, just to keep it simple. What we can do is attach an observer to that. So the observer takes two parameters, an activity and an actual callback. Now, this argument is very interesting. Normally, you're not supposed to pass activities around because they'll leak, but live data is special. Live data is aware of the activity lifecycle, and in fact, it becomes aware of it because you passed an activity into it. The observer it's also parameterized by stock price. When it receives a stock price, what we're going to do is reach into those views and update it. So this is a little bit better here. This is getting better because now we've abstracted away the data source. We don't know are we using Firestore? Are we using Realtime Database? Are we using an in-memory database? Are we using SQLite? We don't know. We don't care. The activity shouldn't care about these things. So this is getting better. But we still have this nagging detail of where did we get that live data from. But I'll say a little bit more about how live data becomes or responds to activity lifecycle changes. So in your activities on stop, what happens is live data becomes inactive, and it will not distribute changes to the live data anymore. So all of your observers are still attached. They just don't receive results. And that's good because the users can't see your activity. What's the point of distributing a result that they can't see? Likewise, when your activity becomes started again, all of those observers that are attached become active again. So they'll start reflecting the changes that are happening within your live data. If the activity goes away and never comes back, like it's gone, during onDestroy, live data will automatically remove all those activity-scoped callbacks. So you don't have to worry about activity leaks. You can just assign your listeners, your observers in there, and it will just be managed automatically for you. So live data is actually doing a lot of good stuff behind the scenes. So what if we wanted to implement live data with Firestore document updates? So now we're wiring up a live data object that's smart about what's going on in Firestore. So the first thing we'll do is create a class and make it subclass live data and parameterize it by our stock price type. And then what we'll do is we'll pass a document reference into it. Now that document reference is a Firestore implementation detail. So if you remember before, we grab the Firestore singleton instance, we reach into a collection, we reach into a document within that collection. That reference is what we're passing here. This is what live data is paying attention to. So what happens is there's two methods that you have to override when you deal with live data. The first is onActive. This gets triggered when the number of observers on a live data goes from 0 to 1, or in other words, someone cares about what's in this live data. Until someone cares, there's no point in actually doing anything, but it will become active when there's one listener or one observer. And what I can do in this case is reach into that document reference, add a snapshot listener to it, and I'll fill in those dots later, but it's going to return a listener registration, and that's my handle into that listener. And I'm going to hold on to that later, because during onInactive, when the number of observers goes from 1 to 0, meaning nobody cares what's in this live data anymore, what I'll do is I'll just remove the listener. So when the live data becomes active, we want to start listening. We're interested in what's in this document. When no one's listening anymore, we'll just shut down the listener. So pretty straightforward stuff. There's one more thing. I had to fill in the dots from that add snapshot listener. What I can do here is make this object its own listener. So I can have it implement the event listener interface. I can pass an instance of this to the snapshot listener. And that means I have a new method I have to override here. I have to override, or rather implement onEvent. And I'll show you what that looks like. So the implementation of onEvent is going to, just like before, take a snapshot or an exception, either one, not both, not neither. And I'm going to check and see if this snapshot is something, if it's legit, if it's not null and the document exists. I'll create that stock price model like before. And then I'll call a method on live data called setValue. SetValue is the special method on live data. What that does is it not only sets the current value of this live data that it's held internally, it will also notify all the observers. So all those observers that are attached to it that are waiting for this data are going to get it in response to the call to setValue. And of course, if there's an exception, I'll have to do something with it. And of course, you should handle errors. I'm not going to show you every example of error handling. That's up to you. But I'll get to that in a little bit. So there's still two problems to resolve here. We have a good live data. The live data is OK. But the question is, who creates this live data? Who's responsible for making this? Well, there's one important thing to note. That stock price live data object that I just showed you, it exposes Firestore implementation details. It needs that document reference. So whoever creates the live data has to know about the actual underlying data store. Now remember, views should know nothing about the data store, and vice versa. Your data store should know nothing about the views. That means the activity can't actually make this object. If it knew how to make this object, it would have implementation details, and we're back to where we started. So the other problem is that live data loses its data on configuration change. So if that activity gets reoriented, you know what a configuration change is. The most common one is reorientation. So you go from portrait to landscape. Your activity is going to get destroyed and then rebuilt and come back the way it was. The problem is the live data is also going to get destroyed along with it. It'll become inactive. So all that data that's stored in there goes away. And I'd rather not have that happen. If at all possible, I'd love for that live data to retain its data so that the next instance of my activity can pick up where it left off without skipping a beat. Yeah, that's what I just said. So to address these issues, we have ViewModel. So ViewModel is another Jetpack component. What it does is it survives configuration changes. That is its superpower here. And it's not so much the ViewModel itself, it's sort of the infrastructure that's provided by ViewModel. So the saved ViewModel instance will get shared as an activity goes through configuration changes. Even though the activity is destroyed and a new one takes its place, it can reuse the ViewModels that were created in the first one. It's also shared and managed. So the system manages the scope of these instances, and they may be shared between fragments within an activity. You don't need to know about that, but it's like the fragments don't need to each know that they're sharing each other's view models necessarily, but this can happen. And they're also lifecycle aware. So any view models that you create in an activity, when that activity is backed off the stack and goes away for good, those view models will go along with it. They're not held indefinitely. So it's doing a bunch of things behind the scenes for you that you don't have to worry about, that you used to have to worry about. It's also worth noting that view models aren't persisted to disk and stored back. It's the exact same view model object that's shared between each activity instance. To visualize this a little bit better, imagine there's that stock tracking app I showed you before. Everything's fine. There's a view model in there. And that view model contains a live data that's feeding these views. So you can imagine this live data here is like feeding all these views. All these changes are getting spread throughout all the views in this activity. But if there's an orientation change and the activity goes away and comes back in landscape, well, this activity needs to pick up where it left off. So what Jetpack does is it says, hey, view model, you were over there before. Now I'm going to reattach you to this new activity, and everything's good. So that live data can now immediately start feeding those views again. So how do we implement a view model that yields a live data? That's what we want. We want a view model that can deal out instances of live data so we can populate our activities. So what we're going to do is subclass view model, and then we're going to invent an API for ourselves. This is not a set API. This is just one that I invented for myself. We'll create a function there called getStockPriceLiveData, and it takes a ticker. And what this is telling the view model is I have an activity that's interested in live updates for a particular ticker, and it'll return that stock price live data. Now, what I'm going to do also in here is introduce the concept of a repository. The repository is a pattern that's commonly used to keep all of the implementation details of your underlying database, so Firestore, Realtime Database, or SQLite, or whatever you're using. All that goes into a repository. And I'll be a little bit hand-wavy about that right now. We'll just say that there is one. You should probably find it through dependency injection. You probably shouldn't code it up right here. But again, dependency injection is something I won't be too opinionated about today. But all that said, let's just say that stock data repository is an interface, meaning this is not concrete, this is abstract. And what this lets us do is define different kinds of repositories out there, one for each type of database we want to support. So what we'll do is we'll essentially proxy through to that repository. The view model says, I want to get a live data for that yields stock prices. What I'm going to do is say, hey, repository, you know how to do that, right? You do that for me. You create that live data. And that's fine. But the one thing I'm not showing here that if you look inside my code that you'll see more information about is the view model should retain and reuse this instance. As you're seeing this code right here, it's calling through to the repository every time. We don't need to do that. What you should probably do is think about making a map and mapping the stock price live data to the string ticker. So that the next time you come in here, check the map, see if it exists, grab it, return it. Anyway, that's more code than I'd like to show here. But we still have to worry about this repository. Let's say we want a repository that's backed by Firestore. We want those stock ticker documents, those live updates to those documents to come through. So what we can do is implement this interface, which means we have to override a function, the same function that's in the interface. What we'll do is grab a hold of the Firestore singleton instance. And again, dependency injection, probably the way to go here. I'm just including it right here for simplicity. And what we can do is use Firestore, reach into the stocks live collection, reach into the document ticker. Now we have a document reference. And then we'll just hand that off to the stock price live data from before. So if you can remember before, that stock price live data implementation takes a document and will then attach listeners to that document as needed. So what we have right now is a great team of players. We have live data for distributing live updates. It's observable, and the views are observing it. We have a view model, which survives configuration changes. We also have a repository pattern, which is our guts of our data system. All of that's abstracted behind there. And we have Firebase backing those guts, so we have that cloud-hosted service. Between these four components, you actually have a really good chance at making a very usable, very testable, given that you want your classes to be small and testable. This facilitates usable and testable apps. And what we did right here is actually implement this architecture pattern. Now, if you go to the Android Jetpack documentation, you will see this actual picture. I ripped it right out of their docs. And what we did is we actually just built this, except we're not using Room as a persistence layer. In the Android documents, they suggest that if you're making API calls to something, you should persist them in Room so that you can cache them and read them later. It turns out Firebase has its own internal caching mechanism, so when you're using Firebase as the backend, you don't need to persist the results of your queries. It's all handled internally inside the SDK. All that said, you could still use Room if you wanted, but I'm just depending on Firestore's own internal persistence mechanism. So this is what we've built. Except we've built everything so far. We have a view model, we have a repository, we have Firebase, except we need to glue them all together in the activity layer. So how do we implement this activity that glues all these things together? Well, what we can do is start out with our standard Android activity boilerplate. So we have an onCreate. Whoa, it's getting dim in here. OK. That probably makes it easier to see, actually. So we'll inflate and initialize views. That's all boilerplate stuff. Now what we'll do is we'll get a view model from Jetpack. It's still getting dimmer. It's mood lighting, isn't it? I like this. The magic here, there's all kinds of magic going on here, and it's right here in this view model providers class. View model providers has a static method called of. You pass it the instance of the activity that's currently in play here, and you say, hey, I need a view model that's of the type stocks view model. So that's Kotlin for give me the class object, the Java class object that represents the thing I want. So view model providers, it's smart enough to create a new instance of your stocks view model if it doesn't already exist, or reuse one from the prior activity. It's doing all of that in one line. All you have to do is pass an instance of your activity to the of method. Now we have a view model, and that view model contains the live data, or rather, it can yield the live data we're looking for. So we'll call the get stock price live data. This is a very Java method name, isn't it? Get stock price live data, pass it the sticker we want. The sticker, the ticker, the hot stock. The ticker we want, we'll get a hold of that live data. Then with the live data, we'll attach an observer. And again, we're going to pass an instance of the activity. We're going to pass it the observer that should respond to changes in the live data. And we'll reach into our views and update them from there. This is good. This is good architecture. Notice we already have an activity that responds to live changes in Firestore, but it's like a dozen lines of non-boilerplate code. Not even that, just like 5 lines of non-boilerplate code. ViewModel is doing all the hard work of retaining on configuration change. Live data is doing all the work of distributing to all the observers. And the observers just saying, hey, give me a stock price object, I'll go populate a view. That's all there is to it. The underlying repository is completely hidden from this activity. We don't know if it's Firestore or Realtime Database or SQLite or whatever database you want to use. So this is good. But we have to come back to dealing with errors. You noticed before that I kind of glossed over all those errors. Anytime there was an error, I just put a to-do. Of course, in Kotlin, a to-do will crash your app, so don't do that. But how do we deal with errors? Well, the problem here is that if you have a live data parameterized by stock price, well, how do you send an error through that live data? I mean, all it sends is stock prices. It doesn't send exceptions. So how do we get this thing to actually propagate an error if there is one? We need those errors to bubble up so we can change our UI. And again, repositories shouldn't know about your UI shouldn't know about your repository, so we need a way to bubble up those errors from the repository into the UI. And we can do this by just creating a data class. It's kind of like pair. If you know pair, it's just two things. I call it data or exception. It takes a type T, which is the normal success type, and then some exception type, which represents an error. So with data or exception, what we can do is type alias that to something called stock price or exception. Now what we have here is a data class that gives you either a stock price or an exception. You have to check, but the point is now you can bubble up that exception and let the UI deal with it in whatever way makes sense by showing an error or telling the user, you're doing it wrong, come back again later. So now our live data can be parameterized instead of just by stock price or exception. So you'll see this pattern throughout my code. Anytime there could be an exception, I'll let that bubble up. And I do it through the data or exception pattern. So right now, all I've shown you is how to listen to results to a single document, which is helpful. But let's be honest, when you're dealing with a database, you want to do queries against it. One document is not really that helpful. It's helpful sometimes, but really what you want to do is query and get all the items and then show them maybe in a RecyclerView or some other format. So how do we do that? Well, with Firestore, queries work just like documents, like I described before. So say one client makes a query to Firestore and says, give me a set of documents that match my criteria. Well, it turns out if any one of those documents changes, that gets reflected in the query results. If a document is added to the results, that gets reflected. If a document is removed, that gets reflected. The query itself is live. It's constantly changing if your data is changing, which is super helpful for building very live UIs. Now, I'll remind you how Firestore queries work if you don't already. We need the Firestore singleton instance. We need a collection. Every query starts with a collection. If we just say collection, that query gives you everything in the collection, which may or may not be what you want. If it's too many documents, maybe you want to filter it using a where. So you can say, well, give me all the stocks where the price is above 100. So we have kind of a stock leaderboard going on here. And maybe we want to order that by price. We don't want them in any order. We want them in descending order because we want to show the most expensive ones at the top and work our way down. Now, this is a query that we can execute very simply by calling get. Get yields the entire set of documents that satisfy that query. But it only yields one set of results. So if you listen to the results of this get, what you'll get is a snapshot query, or I'm sorry, a query snapshot. That query snapshot lets you iterate all the documents that satisfy the query. But I want live results. I don't want just a static set of results. So instead, I can add a snapshot listener to it and then pass an event listener to that. And that listener can receive updates to the query as it happens. This represents ever-changing results if they do actually change. So how do we make an event listener? All we have to do is implement the event listener interface with a query snapshot. So what this does is it gets us a callback that gives us either the query snapshot if there were documents, if there was a successful query, or an exception, just like we saw before. What we can do is reach into that snapshot, that query snapshot, get a list of all the changes that have happened. So this is a delta since the first time it was called, and then see what kind of change it was. So the first time this is called, what will happen is all the documents that match the query are actually all added. So you'll get one added callback for each document that initially is in the search results. And then after that, if any other documents are added, modified, or removed, you'll get callbacks for those. So that's a good way of staying up to date on what's changed. There's only one problem, though. If we're only ever processing deltas like this, only new things that have been added, modified, or removed, we can't really propagate through that through a live data. Live data wants to do the entire state of the results all at the same time. It doesn't do deltas. It does entire state at once. And so if you want to make a live data with document change or a live data with a list of document changes, that's not really going to work for us. The listener, the receiver on the other side of the live data would have to remember everything that happened before it and somehow maintain its own state. We don't want to do that. So we actually want a list of stock price objects. That would be better, as long as the stock price objects all satisfy the results of the query all the time, which they should. But that's still kind of not good enough, because remember, a query could have an error. So maybe what we need is a live data with data exception that either is a list of stock prices or an exception. So we've got to handle errors. This is what it looks like. But we're actually going to add one more layer of complexity in here, and I'll tell you why later. But I'll introduce this query item generic in here. So what this is saying is we have a live data that contains a data exception. The data is a list of query items of stock prices or an exception. And we're in generics hell right here. Do you ever write generics that are that deep? I don't like that. This works, but what oh, by the way, query item either has the item that you're looking for, the type T, so the stock price, and it also assigns some ID. And this ID is helpful later, and I'll go into that in a bit. But we need to escape this generics hell. I don't want to type all those angle brackets all the time. So what I can do instead is type alias query result or exception. Now we're down to 2 elements, and those elements are either a list of query items of some type or an exception. We can go even further and say, well, I actually want stock price query results, which is a query results that contain a list of stock prices or exceptions. So now we're down to just one simple type. Kotlin has saved our butts on this one. It's saying, well, I'll let you use type aliases and kind of scrub out all those generics you might not be interested in seeing all the time. So this is what we need to generate now. We want a live data that gives me errors or results of lists of query items of actual implementation data. So with Firestore, what we need is a live data that responds to Firebase queries. So we'll start implementing it. Well, we'll start with a type alias that says what this is going to generate is either document exceptions, a list of document exceptions, or an exception. That's what we're saying. That's what that generic is saying. What we'll do is get a hold of that Firestore query, and then we're going to pass it to Firestore query live data. And the live data implements this interface, or I'm sorry, the generic type is document snapshots or exception. So what do we got to do to implement this? Well, like any live data, you need an on-active, you need an on-inactive. You need to know when to start and stop listening to the query. And then you can use the listener register that I showed you before, except we're listening to the results of a query in its entirety, not just a document. And again, the class is going to implement its own event listener. Its own event listener I'll show you on the next page. Oops. Nope, it's not the next page. It's this page. So what we're going to do here, instead of looking at the document changes part of the snapshot, we're just going to look at documents. Query results has a property called documents, which is the entirety of all the documents that satisfied the query. We're ignoring the deltas. Just give us the raw documents. Then I'll make a list of those documents and send those on. OK, so this is a live data that will let you respond to new documents. But to go further with this, we actually wanted a live data that was stock price query results. But what we have is a document snapshot or exception. We need to do some transformation here, and I won't show you that. You can go into my code. There's actually a thing called Mediator live data that lets you transform the contents of one live data into another live data. Using this Mediator live data, we can parse the contents of those documents and create stock price objects out of that. Again, it's in the source. It's kind of boring, but it's helpful. And then what we're going to do is observe that new live data, stock price query results, and then update the RecyclerView adapter. Because if you don't know how many results, or if there's going to be a lot of results, you probably want a RecyclerView, right? I mean, you don't want to stick them all in their separate views. But if you're using a RecyclerView, and I imagine most of you have, you probably know that in order to tell the RecyclerView to refresh its views, you call notify dataset changed on an adapter. Now, if you write this adapter yourself, what's going to end up happening is you'll refresh all of the views all of the time. And that is, to be honest, kind of janky, right? If you have constantly updating results, you only want the parts of the results that actually changed to be refreshed. You don't want to refresh the entire thing every time. Trust me, I tried it this way at first. It was fairly janky. So what I ended up doing to solve this problem was use a RecyclerView extension called list adapter. This is not the same list adapter that you find with, what was the original one, the list view. List view is deprecated, but there's a new thing called list adapter. I don't know if you've seen this. I actually encountered this for the first time recently. It's relatively new in the support libraries. What it does is magic. It's as best as I can describe it. And I'll unpack a little bit of what the magic is, but it handles a lot of, basically it handles the jank for you as long as you do one thing. When you have a list adapter in hand and a list of objects in hand that you want to display, all you do is call submit list on it. And what it does is it goes through the trouble of figuring out exactly what changed in that list. So what it does is it looks at the before list, looks at the after list, marries up all the items and says, well, that item changed, that one didn't, and this one had something, and there's a new one. And so what it does is it only emits the adapter events that are required to minimally support the changes between the old list and the new list. So that's very handy. And it's all doing this on a background thread, so it's not, all that computation is going to be very much non-janky, just there's going to be some latency. Now there's a catch here. What is the catch? Well, all you have to do is implement one abstract class. That's all you have to do to make list adapter work. And that's something called diffutil.itemCallback. This is an abstract class that is parameterized by the type of thing that's in your list. So it's some type T, in our case it's stock price. What we're going to do here is, actually, this is not an implementation. This is the actual abstract class itself in Java that I pulled right out of the support library. So there's 3 methods in this abstract class. One is are items the same? What this does is when you override this, you return true if old item is the same as new item. So this is part of the diffing algorithm that it uses. It's going to pass pairs of items in there and say, are these two the same item? And how do you tell if they're the same item? Well, we'll get to that. Now, if the items are the same, the differ says, okay, if this is the same item, are the contents the same? Do they actually represent the same data? And if it is, you have to check this yourself. If they are the same, it's going to go even further and say, well, give me the change payload. Tell me exactly what fields changed in these 2 objects. And this is optional. And I don't need to use this. This is if you're like hyper-optimizing very large objects with individual items that might change. You don't have to implement this, it's optional. But it is imperative to make sure if your items are the same, you should know it. And if your items contain the same data, you should know it. So now let's do this with query item. Remember, query item was that extra level of abstraction that I added before. With query item, again, you have some item, some type T, and you have an ID, a unique ID for that object. You can use this with diffutil to create one implementation that rules them all. If all of your query results are all generating query item types and they're all Kotlin data classes, this is the only thing you need. This implements diff callback for all query items for all Kotlin data objects for all time. And here's how it works. The implementation of are items the same just checks to see if the unique IDs are the same. That's all it does. They're just strings. All you have to do is figure out what the ID is of the item. In Firestore, it's really easy because every document already has an ID. Just stick the document ID into that field and you'll be fine. And then are contents the same is implemented simply by doing a structural comparison between the 2 objects. Now, in Kotlin, this is actually calling the .equals method on your object. Now, .equals doesn't have much of an implementation in Java. On its own, it doesn't really give you deep structural equality. But for Kotlin data objects, this is more magic. For Kotlin data objects, it's literally comparing the contents of the 2 data objects field by field, deeply checking for equality. So Kotlin is doing all the hard work for us. As long as we're populating a data class with the fields that we're interested in, this works for everyone for all time. So love this. This is saving a lot of implementation detail. OK, so what does this actually look like? Well, in my app, I have this stock price history tracker screen. But this is a RecyclerView. And what it's doing is it's doing a query for all of the ongoing history changes in this object. And you can see the RecyclerView is pushing and animating down all of these items. I didn't have to do anything. All I have to do is tell the RecyclerView, I want new items at the top, and I don't want the user to interact with it. So this is actually a very helpful and live view. Actually, this should be implemented by a graph more than anything else, but it illustrates very well how you can make list adapter on top of RecyclerView, on top of live data, work very, very well. And I will detour a little bit and say, you have to ask yourself, do you really need live query results? That screen over there was handy, but is it very practical? I mean, do you want the user to actually interact with that? Well, it's fun to watch, but it's bad for the user to interact with. If your things are moving all around the screen and you expect them to touch one, there's a really good chance that they may miss it, right? So you saw all those things being pushed down. If I wanted to touch one, I might end up touching something I didn't want to touch and then back out and then can't find it again. And that's a fairly terrible UI experience. So as an engineer, you need to be aware of that. It can be frustrating, and it's probably not so bad for append-only results. So those stock history list is an append-only result. A history item becomes static once it's set forever. It's only ever accumulating new history items. So it's not so bad for that. If your items can be shifting and changing in priority, probably not a real good option for a live data list like this. Although, again, if the user doesn't have to interact with it, it might be kind of fun to look at. So if you're implementing something like this and you don't want the user to have to interact with dynamically changing results, consider using some sort of a refresh indicator instead. So if you detect that new items are coming in your live data, maybe just show a little button or something saying, hey, there's new results, touch this, and they can choose when they want the list to refresh. So anyway, I'm just being opinionated about UI right here. OK. So we've gone through all the major components. We've got live data ViewModel, we've got repository, we've got, actually there's view binding going on in there. I didn't show you any code, but in my code there's view binding going on. But there's another way to synchronize data, not just live, but maybe you want to use, maybe you want to have some sort of background sync for offline use. Now, I'll remind you, Firestore and Realtime Database have an offline data cache. So if you did a query, it pulled down all this data, you can query it again without requiring a connection to the server. So we know offline data is cool. People kind of expect it nowadays. They expect their app to work well when they don't have a connection. And mobile connections are pretty flaky, we have to admit. So let's say, here's a use case. Let's say I want to browse stock prices after the market closes on my subway ride home. And my subway doesn't give me really good connectivity. Now, when do US markets close? Is it like 4 or 4:30? 4:30? Something like that. Which is right before work ends, right? So if you leave work at 5, you hit the subway, you maybe curious about how your portfolio looks. So you want to be able to browse current up-to-date stock prices. But the user maybe hasn't launched the app. You don't want to make them remember to launch the app. It should all just be there in the app ready to go. Realtime Database and Firestore have offline caching built in, as I said. The question is, how do you sync data when the app isn't running? So if the user hasn't launched the app and it doesn't have a process sitting around doing stuff, how do you get that sync to happen at the time you want it to happen? Well, all we need to do is schedule some sort of a data sync, right? If you can schedule it, you can run it, and you can do that using 2 choices. So for background sync, you can periodically poll. So you can say, hey, client, go get me the latest stock values that I'm interested in. Just go do them on some schedule. That's OK. You can also have a backend notify the app when new data is available. So you basically have push and pull options. And no matter which option you want, Work Manager can help you with that. So with Jetpack, there's a new architecture component called Work Manager. It's still in alpha, I believe. But what it does is it lets you schedule work. So you can indicate time of execution and the period of execution. So you can have a daily task or an hourly task. You can't necessarily schedule the exact date and time. You can schedule on a delay based on the current time that you know. But basically, you can do periodic work. You can give it constraints on how to work. So you can say, well, I need the battery to be good, and I need an internet connection in order for this job to run. If I don't have those, don't even bother running it. Don't fire up the CPU, and don't fire up the device if I don't need to do this. And you can do work chaining. So if you have a very complex series of tasks to be executed either in parallel or serial, you can express that as well. So let's say we want to schedule periodic work with Work Manager. We want to go off and get the most interesting stock prices. So what we can do is first build a constraints object. And this constraints object is manipulated by a builder. And what we can do is say, I want to be connected to the internet. That's important. No point in trying to query Firestore if you don't have a connection. Also, I want there to be good battery. I don't want to waste the user's battery if they're below 15%, I think is what it is. Then using those constraints, what you want to do is use a periodic work request builder. And this is Kotlin sweetened a little bit. You can say, well, what I want to do is every 1 day run the job specified by my constraints. And then you can reach into the Work Manager singleton. You can enqueue periodic work, and what you do is you just pass it off the request that you wanted to perform. And this keep right here, existing period work policy, all this is saying is if there was already one scheduled, keep it in the queue. I think you can either keep or replace, but you'll have to make a choice there. So this is a pretty easy way to, once you kick this off, the device is just going to, your app is just going to do that. It's going to wake itself up every day, synchronize, and then go back to sleep. But you don't really have a guarantee about when it executes. I'd rather have it execute when I know the market prices have stopped for the day. That would be the best time to synchronize. So I think in this case, for my use case, periodic work is not really the best option, again, my opinion. Periodic work can't be scheduled like cron. It's not exactly cron-like. It's just periodic, like I said before. So you could try to remedy this by having an overzealous sync period, so you can sync every hour to try to get the latest one, but that's not really what I want either. I could replace periodic delayed work, or I could replace periodic with delayed work, but I have to reschedule my next run after each prior run. I don't want to write that. That's boring. It also depends on the client knowing when the markets close. So you're baking business logic into the client that maybe it's not best suited to have. And there's another constraint here, or there's another snafu here. Individual stocks may still be trading in after-hours trading. So if you've ever noticed, if you follow the stock market, stocks may close at a time, but then there's like extra trading as like news trickles in or something like that. I want those extra hours. I want those after-hours prices as well. That's more interesting to me. So in this case, server push is much better. I'd rather the server tell the client when to fetch its stocks, not the client try to guess when it should fetch from the server. So the server knows when the trading stops, presumably, right? It knows when the final bell has been rung and all the after-hours trading is done. The app doesn't need to schedule anything at all. So what I can use is Firebase Cloud Messaging to notify the app. So Firebase Cloud Messaging is another product within the Firebase suite. It basically is server push messaging. So what I can do, if I can push the message saying a particular stock has stopped trading for the day, then the app can schedule a synchronous or some sort of a sync with Work Manager. So this is my preferred way of doing it, and that's what I've done in the app. To be a little more graphic about this, imagine you have Firebase on one side and you have two different devices, each interested in two different tickers. So the first device is interested in ticker 1 and 2, and the other one's interested in 2 and 3. The easiest way to do this, I think, is to have Firebase broadcast to topics. So what I've done is create a topic name that's based on the ticker that I'm interested in. Firebase can broadcast to those topics, and the device can subscribe to those topics. So the device, with some knowledge of the user's portfolio, can say, I know whenever a message comes in for one of these tickers, I want to know. Let me know, and I'll schedule a sync of that data. So doing the actual FCM work is pretty straightforward. All we need to do is, well, there's a few steps, but this is the most straightforward one. We can subclass Firebase messaging service and expect a data payload. So you send JSON into FCM, and then that gets sent back to a remote message type. So what you have to do is parse this remote message, look into it, see if there's a ticker that I'm interested in. If there is a ticker in this message, what I'll do is I'll synchronize the ticker. That's pretty straightforward. So how do we synchronize the ticker? Well, we want to schedule one-time work using Work Manager. So again, to use Work Manager, all you have to do is create some constraints. So we want networking, we want good battery. The other thing we want to do is pull the ticker. Well, actually, this is a little bit different. Work Manager will persist the work that you tell it to do, but it needs its arguments to also be persistable. So what we're doing here is creating a map and mapping ticker to the actual ticker we're interested in that we're going to call toWorkData on that. And that's a special Kotlin syntax that gives us a data object. And that data object can be persisted on disk so that if Work Manager can't do it now, it can at least do it later by loading that off of disk. Then we kick off the work request, so one-time work request builder, give it the constraints, give it the input data, so the name of the ticker, and then we go off and actually do the work. So Work Manager get instance, all we do is we pass it we're going to give it, this is unique work. So unique work is a little bit different than the periodic work that I showed you before. We're going to give it a name, and we're going to call it, we're going to base it on the name of the ticker. And it's saying existing work policy replace it. If you had something else already queued up for that ticker, replace it. Just use this one instead. Replace that old work with new work. And then we enqueue that. And so what it'll do is, in the best possible circumstance, it'll just work right now. It'll do it in the moment. But if it can't complete for some reason, it'll retry for you, which is super handy. You don't have to write any of that logic. But what we do have to write is some sort of a sync worker. We have to write the worker code for this. And I've totally redacted this out. You're tired of getting Firestore queries shoved at you. So you do your Firestore query here, and then you return success or retry or failure. Now, it's an important thing to note here. Right now, the Work Manager APIs require you to be synchronous, meaning you can't return a result until you know the result of it. And those Firestore APIs are all asynchronous, so you need to put in some little extra code there to make sure this method doesn't return before Firestore's asynchronous results happen. And again, if you look at my code, you'll get a strategy for that. It's basically using a what is it? I can't remember the synchronization primitive in Java. But basically, we're turning async work into synchronous work. And I've talked with the folks at Google who make this API, and I said, actually, we'd rather return a future. We'd rather return something that eventually resolves into results rather than immediately resolves. So this may change in the future. There's lots more in the code repo that I linked to earlier. You can get it here. I'm constantly working on it. I'm giving this talk a number of times in the future, and I'm going to be evolving this talk as time goes on. The implementations are both for Realtime Database and Firestore. So Firestore is in beta. If you don't like using beta services, consider using Realtime Database. Then maybe migrate from one to the other. Shows you how to sync individual documents and nodes and queries. There's also an illustration of using Jetpack paging to implement infinite scroll. Now, my app doesn't show lots and lots of data, but it shows the code that lets you do paging and keeps adding pages to results and populating a RecyclerView from that. So you can effectively scroll forever for as long as you have data backing this request. The backend, there's a backend implemented in TypeScript for Node and Cloud Functions. So I actually work very closely with the Cloud Functions team. Cloud Functions is a serverless compute engine that lets you write and deploy code where you don't have to manage servers. It just runs it in response to changes. Kind of interesting if you like that sort of stuff. I do. I'm an Android developer, but I like doing backend stuff as well. The goal here with this project is to derive a library of patterns to eventually add to Firebase UI. So if you're a Firebase user, you probably already know about Firebase UI. It gives you some great UI tools that you don't have to write, that does a lot of sort of like hard work for you. I'm hoping that a lot of the stuff I just showed you here will eventually get rolled into that. And as usual, stay tuned for more. So that's all I have. Thank you for your time. Thanks for sticking around during lunch.